Okay, so let's solve a system of equations in three unknowns by determinants. And first of all, I almost wish I'd turn a thicker color on here, but this is supposed to be a vertical straight line. And likewise right here, the software I used wasn't working for me when I made this. To evaluate a system of three equations in three unknowns using determinants, I'm going to go down here before I look at this problem right here. I'm going to go down here and tell you that Kramer discovered that to solve for x when you have a system that, I'm going to go ahead and set these up, that you'd have the a values in your denominator, which are the numbers in front of the x's. You'd have the b values in the middle column, which are the numbers in front of the y's. And now we'd have what's called the c values, because those are the numbers that are in front of the z values in this case. And then in order to solve for x, you'd put your d values, which are your constants, on the right-hand side. And that's how you'd solve. Again, like before, the b's would come up in this numerator, and the c's would come up, and you'd evaluate, this should be a 3. You'd evaluate this numerator and evaluate the denominator, and then do the division. But what Kramer discovered is that to do the process, there's 6 multiplications to be done here. The first is to take, I'm going to go with this denominator, is to take a1 times b2 times c3. And I'm not going to be able to write this all out, but I might start it down here. A1 times B2 times C3. And then add, Kramer discovered that you needed to take B1 times C2, but you had to come over here and multiply that by A3. So what Kramer did is copied this column right here, copied it over, and discovered that he'd take B1 times C2 times A3. And then the next would be to copy the middle column here, the b's, over here, because next Kramer had to take C1 times A2 times B3. And I just am not showing you the process of why Kramer, and that's a long algebra proof to do that. C1 times A2 times B3. Add all those up and then subtract these products. So Kramer said next you'd have to subtract, and I'm going to put in parentheses, A3 times B2 times C1. But it's the sum of these diagonals. So here it'd be B3 times C2 times A1. And then finally the last one would be C3 times A2 times B1. Yikes. Well, let's just go ahead and evaluate a determinant up here. So in other words, copy the first column, a -2 times 5 times 4. Copy the second column, 4, a -10, and a -8. And there are 6 products you have to find. You have to find that product right there. So a negative times a negative is a positive. Here's a positive. And so this is 20 times 2 is 40. And then the next diagonal is 4 times 4 times 4, which is 64. And then the next diagonal, there's a negative times a negative in that diagonal, so it's positive. And 5 times 8 is 40. And then you need to subtract the other diagonals. So right here, 4 times a -10 times a -1 would be a positive 40. This -8 times 4, which is a -32, times a -2 is a positive 64. This is a fluke that this determinant turns out to have the same factors here. And then 2 times 5 is 10, times 4 is 40. And whether or not you happen to notice, actually this is 144 and this is 144, and when you subtract that, the value of this determinant is equal to 0. Next time we do this, I'm going to show you how the calculator can help it do this for us. But let's go ahead and evaluate this system right here, and let's solve it for x. Let's do it by hand first. So in the denominator, I like to do those first. The 2, the 4, and the 8. Just strip these numbers right here. Positive 1, negative 3, negative 2. This is a problem that we've done already once. This one's a negative 1, negative 2, negative 3. We did it in the last section. I'll tell you what the answers were in a minute. The D values are the 4, the negative 2, and the 3 right here. Those go over here. And then I bring up this column, the 1, the negative 3, and the negative 2, this negative 1, this negative 2, and this negative 3. I'm going to go ahead and tell you that when we did this problem algebraically in the previous segment, we got x is a half, y is 2, and z is a negative 1. So let's go ahead. We can get rid of Kramer's hypothesis here, and we did not prove it. Let's go ahead and evaluate these two determinants. So this column's got to be copied here. So 4, negative 2, and 3, and then this column, 1, negative 3, and negative 2. Let's just go ahead and do these products. So let's go these three right now. If you don't mind, I'm going to use my highlighter. So let's see. This is 9 times 4, which is 36. 1 times negative 2 times 3 is a negative 6. 3 negative sign, that's negative, and it's a negative 4. Then I'm going to subtract. Again, remember, it's the 3 diagonals. It's this one, and this one added together, but then a subtraction sign in the middle. So this would be a positive 9 when you multiply those together. Negative 2 times the negative 2 is a positive 4, times 4 is 16. Negative 3 times negative 2 is positive 6, times 1 is a positive 6. So let's see, here this is a 26, and this is 25 and 6, 31, I believe. And so the numerator for this problem turns out to be equal to a negative 5, 26 minus 31. All right, let's go grab this denominator. So let's copy this column, 2, 4, and 8, the 1, the negative 3, and the negative 2. And let's get this product, and that product first. So this one is 9 times 2, or 18. 1 times a negative 2 is a negative 2, times 8 is a negative 16. And then these two negative signs become a positive, and 4 times 2 is 8. Then we have to subtract. Let's get these 3 diagonals. I find this to be easiest to just do by hand. So 8 times a negative is a positive. 8 times 3 is 24, times the 1 is still 24. Negative times a negative is a positive 4, times 2 is 8. And a negative 3 times 4 is a negative 12, times 1. And so this denominator turns out to be, this is 10, it looks like, and 24, 26, 36, 44, I believe. I've probably done something wrong here. Oh yeah, that's 12. 24 minus 12 is 12, and 8 is 20. So 10 take away 20 is a negative 10. And remember, we were solving for x, and a negative divided by a negative is positive, and 5 over 10 is 1/2, and that's what we got a bit ago. Now, if I wanted to solve this by determinants to get my y value, and I'll go ahead and bring this so you can see it. When I solve for y, my numerator will have the 4, the negative 2, and the 3 in the center now when solving for y. And then my denominator had a 2, 4, and 8 in the first column. I'm bringing that up. And my denominator had a negative 1, a negative 2, and a negative 3 in the third column. I'm bringing that up. And the denominator is the same when solving for y. So let's go ahead and finish this one. So a 2, a 4, and an 8. this column gets copied. This red column, a 4, a -2, and a 3 gets copied. So now I'm going to take this product, and this product. So let's see, this one is 12. And then this product, 8 times 8 is 64. There's one negative sign, so a -64. Here, that product is 12, and it's negative. Then I'm going to subtract this diagonal, and this diagonal's products. So there's two negative signs here. 8 times 2 is 16. Here there's just one negative sign, so it's going to be 4 times 3 is 12, and it's negative. This is just, again, one negative sign. 16 times 3 is 48. And don't forget, the denominator for this problem is still going to be the 10 minus the 20 up above, which is a -10. Let's do this up here. So this turns out to be a -64, and this would be 4, and that would be a -44. So we add 44 here to a -64, so it looks like we get a -20 over a -10, and y would, a negative divided by a negative is a positive, and y would be equal to a +2 that we had gotten already. At this point, I might just go ahead and take an x of a half and a y of 2 and solve for z in any one of these to get the fact that z is equal to a -1. That's solving by determinants. Whew, quite a bit of work. I'm going to be asking you to do a take-home problem where you'll have to do one problem algebraically and one problem by determinants.